Let's jump into some more specific details about the kinetics, folks. Okay, so the type of kinetics that we'll be talking about in this class, they are called Michaelis-Menten kinetics. And so in this kind of framework of kinetics, biochemists have done their best to simplify what's happening so that the math becomes easier. So how do we do that? Well, we set the reaction up in the lab so that we can have these two key assumptions of Michaelis-Menten kinetics. The first is the assumption of equilibrium. So let's take a look at the reaction scheme to the right. You can see we start with enzyme and substrate. Oops, excuse me. Trying to find where my mouse went. There we go. We start with enzyme and substrate. The rate, K1, is the rate of binding to form the enzyme substrate complex. The rate K minus 1 is the rate of dissociation back to just enzyme and substrate separate from each other. These rates we assume are very, very large. We'll assume K1 is very large. We'll assume, sorry, K1 should also be there. K1 is very large. K minus 1 is very large. When they're very large, it means these steps are fast. Okay, so binding and dissociation are fast. K2 is small. So the step of converting enzyme substrate complex into product, right, the reaction, we assume K2 is very small or slow. And this allows the system to reach equilibrium because K1, K minus 1 are so fast that, bam, we can quickly reach equilibrium where the rates of the forward and reverse reaction become equal to each other, and K2 is very slow, so it's not detracting very much from K1, K minus 1. We also assume in Michaelis-Menten kinetics that we have achieved steady state. Okay, so here we have very large concentrations of substrate to make this happen. And so when we have large concentrations of substrate, we can assume that almost all the enzyme is in the enzyme substrate complex. And we'll do Michaelis-Menten kinetics when that concentration of enzyme substrate complex does not change over time. So that is steady state. The mathematical representation of that is to the right. And I want to emphasize the difference here, folks, between equilibrium and steady state, because equilibrium is an idea of rates of reaction becoming equal, and steady state is about the concentration of things not changing over time, which is more of an idea of homeostasis rather than equilibrium. And to just reinforce this, I want to show you a graphical representation of what we just talked about. Where on this graph have we first achieved equilibrium of K1, K minus 1, and where on this graph are we in steady state? So we reach equilibrium right here on the graph, because you can see before this we have increasing concentration of enzyme substrate complex and decreasing concentrations of enzyme. But at this point, we see that the concentration of enzyme and substrate becomes steady over time. So this is where assumption 1 is met if we were doing this experiment in a lab. Now, where is steady state? So steady state is represented by the darker inlaid box that starts at 1 and ends here. You can see after this time, we start having a drop off of the enzyme substrate complex. So this is where assumption 2 is also met. And to reiterate, folks, this is important. These assumptions are important because they make the math easy to do for biochemists. And we will talk more about the importance of the math and the variables that we get from doing this math next.